Welcome to Section 1.1, Precalculus Review I. We will refresh the algebra tools that support limits and derivatives throughout differential calculus. These are the main goals for the section. The emphasis is not only on getting answers, but also on recognizing which algebraic tool is appropriate. Real numbers include fractions, terminating or repeating decimals, and irrational numbers such as square root of 2 and pi. Their positions on the number line determine their order. Parentheses exclude finite endpoints and square brackets include them. Infinity and negative infinity always use parentheses because they are directions, not attainable endpoints. In example 1, inspect each inequality sign to decide whether its endpoint is included. Example 2 shows that interval notation can concisely describe an eligibility rule. The open circle at -4 means that endpoint is excluded. The filled circle at 2 means 2 is included. Therefore, x is greater than -4 and less than or equal to 2. A negative exponent means reciprocal, while a fractional exponent describes a root and a power. For real number work, even roots of negative numbers are not defined, but odd roots are. For rational exponents, the denominator gives the root and the numerator gives the power. In Part C, deal with the negative exponent by taking the reciprocal. These laws let us simplify efficiently. Pay special attention to the operation. Multiplication, division, and raising a power to another power use different exponent rules. Parts A through D use the basic product, quotient, power, and distribution laws. Parts E through G require applying the laws to every factor and rewriting negative exponents positively. These expressions combine several laws. Work systematically. Deal with coefficients, then each variable, and finally rewrite any remaining negative exponent. In Part A, multiply coefficients and add exponents. In Part B, divide coefficients and subtract exponents. In Part C, distribute the outside exponent to every factor. For Part D, first subtract the exponents because the bases agree. Part E is a power of a power. In Part F, the negative exponent flips the fraction before the exponent is distributed. The first two parts translate rational exponents into roots and powers. In Part C, extract the largest perfect cube from both the coefficient and the variable power. Radicals can be separated across multiplication or division, but not across addition or subtraction. The positivity assumption lets us extract even powers without absolute value complications. Each radicand is rewritten as a perfect power times what must remain under the radical. For the fourth root, every factor is already a perfect fourth power. In Part D, multiplying the radicals produces a perfect square. In Part E, cube roots handle the negative numerator normally because the index is odd. Rationalizing multiplies by 1, so the value does not change. Rationalizing a numerator will later be useful when working with certain difference quotients. Like terms must have identical variable parts, including identical exponents. Only their numerical coefficients are combined. Distribute both outside factors to every term. The most common error is failing to distribute the negative sign to all three terms in the second polynomial. In Part A, distribute and use the rule that e to the t times e to the negative t equals 1. In Part B, factoring the common factor makes the cancellation easy to see. These identities appear frequently in calculus simplification. When squaring a binomial, don't forget the middle term. The first expression matches the square of a difference. The second uses conjugates, so the two middle terms cancel and leave a difference of squares. Factoring rewrites an expression as a product. Always inspect for a greatest common factor before trying a more specialized pattern. These examples broaden the idea of a GCF beyond ordinary polynomial powers. A common factor may contain a decimal, a fractional power, an exponential expression, or a negative power. In each expression, choose the largest factor shared by all terms. For variable powers, factor out the smallest exponent that occurs. Part D extracts the common exponential factor. In Part E, the lowest common power is negative 1/2. Subtracting that exponent from positive 1/2 leaves a first power inside the brackets. Grouping succeeds when the terms can be arranged into pairs that produce the same binomial factor. In Part B, rearranging the terms makes this structure visible. For a monic trinomial, seek two numbers with the required product and sum. The second example reminds us that extracting a GCF may reveal a monic trinomial. Recognizing a standard pattern can make factoring much faster. The signs in the sum and difference of cubes formulas deserve careful attention. The first is a difference of squares, the next two are perfect square trinomials, and the final expression is a difference of cubes. Solving by factoring depends on the zero product property. This is why we must first rewrite the equation so that one side is exactly zero. First factor out x, then factor the quadratic. Since the product of three factors is 0, set each factor equal to 0. Never divide by an expression that could equal 0 unless that case is handled separately. Moving everything to one side and factoring preserves all solutions. The quadratic formula applies to every quadratic equation in standard form. Before calculating the roots, the discriminant tells us how many real roots to expect. Here A equals 2, B equals 3, and C equals -4. The positive discriminant produces two distinct real solutions. Keep the exact radical forms before giving decimal approximations. There is no need to finish substituting into the quadratic formula. A negative discriminant means the square root is not real, so there are no real roots. Setting net profit equal to 0 finds the break-even times. Factoring shows that the model predicts break-even 1 year and 5 years after launch. Because the parabola opens downward, its vertex gives the maximum. The vertex occurs 3 years after launch, when the projected net profit is $8,000. The graph also confirms both break-even points. Most quadratic formula errors happen before the arithmetic begins. Standard form, correct signs, and a complete fraction bar prevent many mistakes. Context then determines how to interpret the solutions. That completes section 1.1. The goal is not to perform algebra mechanically, but to recognize structure and choose an efficient method. A little factoring can make even a dramatic expression calm down.